Hi, this is Scott, and I'll be giving the final two lectures of this class, the Fundamentals of Statistics and Computation for Neuroscientists. I'll be building off of last week's lecture by Stacy when she went over the Fourier transform and a little bit of frequency analysis using the spectrogram. But what I'll cover in this first lecture is first filtering, so how to isolate a specific frequency component that you're interested in your signal, or remove a frequency component that you don't want in your signal. And the second topic I'll go over is the amplitude of the frequency component. So how can you find out the amplitude as a function of time of a specific oscillation in the signal that you are interested in. First, to motivate why filtering is useful in neuroscience, it's common for us to record electrical signals of the brain like that shown up at the top here, and these electrical signals will have some signal that we're interested, but also some noise. So in this case, if we're only interested in the oscillatory components here between about 9 and 11 hertz, then we may want to filter everything out so that we can only focus on analyzing this narrow frequency component and maybe characterize the amplitude of that component without dealing with the noise in the other frequencies. So in the neuroscience literature, each frequency band has basically been given a distinct name of a Greek letter. So slow oscillations between about 1 and 4 hertz are called delta. Theta rhythms are between about 4 and 8 hertz, and they're commonly recorded in the hippocampus. Alpha oscillations are recorded in the visual cortex and are about 8 to 12 hertz. Beta oscillations are commonly talked about in the motor cortex, and they range between about 13 to 30 hertz. And pretty much everything above 30 hertz is called gamma oscillations, and in some literatures they even subset this to low gamma between 30 and 50, mid and high gamma at other ranges, and high gamma power is also sometimes associated with spiking. So in different instances we may be interested in each one of these frequency components. So last week Stacy introduced the concept of convolution, and convolution will be really important when thinking of filtering. So to refresh your memory, convolution is here on the left, where if we have two signals and we convolve them, then what we're doing is essentially time reversing one of them in case the red triangular signal here, G, and then scrolling that through the other signal to be convolved, F, the blue square. And by shifting the two signals with respect to each other and taking the dot product at each point, this is in essence convolution, and it's expressed by the formula down at the bottom here. And so for filtering, we will want to start with our raw signal x of n and filter it with a function h of n in order to get our desired output y of n, where n here is a sample in time. Let's look at an example in which our filter function h of n, or I'll also call this the kernel, the filter kernel, or the filter impulse response is another name for it. Let's look at the case where we set h of n to be a 10 hertz sinusoid. And our input is also a 10 hertz sinusoid. So if we use the convolution formula to convolve the input function, the input series x of n, with the filter h of n, where both of them are 10 hertz signals, our output y of n will be also 10 hertz sinusoid with about the same amount of power. However, if our input is a 6 hertz signal and we do this convolution, Again, this is by time reversing h of n and sliding that through the input signal x of n. We get out a 6 Hz signal approximately, however it's been very attenuated by this filtering process. The same thing happens if our input is a 35 Hz signal, which is very far away from 10 Hz. So if we convolve a 35 Hz input signal with the 10 Hz kernel, 10 Hz filter, then our output is a very attenuated 35 Hz sinusoid. If our input is a combination of many frequencies, such as what we'd have in white noise, sliding this 10 Hz filter through the function would extract the 10 Hz component from this noise. So the white noise doesn't really have any prominent frequency component, but when we convolve it with a 10 Hz sinusoid, our output is the 10 Hz component of that signal. So what is convolution? With a 10 Hz sinusoid give you the 10 Hz component of that signal. So imagine that our input signal is our 10 Hz sinusoid, and the filter that we're using is also 10 Hz sinusoid, so it's the same frequency. As we shift the filter along the function, the peaks and troughs will line up maximally with one another between the filter and the input signal as we're sliding the filter across the input function. And when that happens, by taking the dot product between these two functions, which is shown down here, so the dot product between, say, 1 and -1 is -1, the product of half, or square root of 2 times negative square root of 2 is -1/2, and so on, then the sum of the product at each time point, or the dot product, will have a high amplitude. However, on the right side over here, our filter is not of the same frequency as our input signal. So the peaks and troughs don't necessarily align in this convolution. So when doing the dot product on the bottom here, adding together the point-by-point product of the signals, then everything will cancel out. So because of this, that is why convolving with a 10 Hz sinusoid will mainly extract the 10 Hz component of that signal. So there are a few different kind of filters that we can use, and I'll go over the 4 main types now. So the first kind of filter we'll talk about is illustrated up at the top here. This is what we call the frequency response of the filter. So we have frequency on the x-axis and amplitude on the y-axis, and this function describes how the filter either attenuates or does not attenuate each frequency component of the signal. So this plot up here is showing the Fourier transform of the low-pass filter. So this filter has high amplitude at low frequencies and low amplitude at high frequencies. This is what we call a low-pass filter. So ideally, this pass band would have an amplitude of 1, so the low frequencies that come in, their amplitude when they go out of the filter has not changed. However, the higher frequencies in the stop band, their amplitude is attenuated completely. So an example of this is a raw signal up top here, which is maybe a 5 or 6 Hz sinusoid with some noise on top. And if we do a low-pass filter around 10 Hz, then we would get the signal plotted at the bottom here. And this could be useful for analyzing event-related potentials, for example. So in many EEG experiments, electroencephalography, they'll be recording and looking for a very low frequency signal in response to a cue or a memory array or something like that. So they won't want to have those high frequency components in the signal, so they will generally low pass their data. The opposite of a low pass filter is a high pass filter, so that's described up at the top again, where after the filtering procedure is applied, the amplitude of the low frequencies is 0, but the amplitude of the high frequencies is 1. They have not been attenuated. So the amplitude is the same in the input for the high frequencies and the amplitude of the high frequencies in the output. So an example of that here is up at the top. We have a signal that has a low frequency trend, some oscillations here that look to be about 20 Hertz, and some high frequency noise up top. And perhaps we don't want this low frequency trend in the signal. So in order to do that, we would do a high pass filter and get the result at the bottom, where now we don't have that low frequency fluctuation in the signal. And this could be useful in our data if we have a reference that's changing voltage very greatly over time, and maybe that's not the physiological activity that we're interested in. A third type of the filter is called a bandpass filter, so that will only preserve the frequency components in a certain narrow frequency range. So low frequencies are attenuated to 0, as well as high frequencies, but in a certain frequency range of interests, the bandpass filter will let those components of the signal through without being attenuated. So these are the components I mentioned at the beginning of the lecture: delta, theta, alpha, beta, gamma oscillations. Usually those are extracted from a signal by using a bandpass filter. And here's an example that has low frequency, mid frequency, and high frequency components. And when we do the bandpass filter just around, say, maybe this is 10 to 30 Hertz, then all we're left with is this 20 Hertz component of the signal. The high frequency noise is removed, as well as the low frequency trend. And the final type of filter I'll mention is the band reject filter, also known as band stop or notch. And this is the opposite of the bandpass filter. So at low frequencies and high frequencies, the signal goes through the filter completely unattenuated. But there is a narrow frequency range in which those frequencies are attenuated completely. So an example of this is to remove the electrical line noise in a signal. So line noise is commonly picked up around 60 Hertz. And this signal at the top has an example of that, where we see maybe a low frequency oscillation in this signal, but it's very heavily masked by a 60 Hertz sinusoid here. So if we perform a notch or a band stop filter at 58 to 62 Hertz, then that will completely remove this very high amplitude, high frequency sinusoidal signal, and we'll just be left with the low frequency component, as well as still the high frequency noise in the signal. An important property of filters is that they are not ideal. And by ideal, I mean if we wanted to design a low-pass filter with a cutoff frequency at 10 Hertz, so ideally we would want it to not attenuate the frequencies below 10 Hz at all, so the amplitude of the filter would be 1 below 10 Hz, and we would want it to completely 100% attenuate the frequency components above 10 Hz. So we would want its frequency response to have a value of 0 greater than 10 Hz. But designing a filter kernel in the time domain of a filter with this frequency response is impossible if we don't have an infinite amount of time, which we never do. So what we do is we design filters, and they would look more like something on the right here, where we have a pass band and a stop band still, but we have a transition region around our low pass filter at 10 Hz. So it will probably attenuate the 8 Hz component of the signal and not completely attenuate the 12, 15 Hz components of the signal, but overall the signal that comes out after we run it through this filter would be more or less what we were looking for, the main low frequency components in the signal. And even if we had our filter kernel as a sinusoid, as we used in the example earlier, that did not completely attenuate the frequency components at the other frequencies. So the filter kernel that we design will have some complex shape. When designing our filters, there'll be a few properties of the frequency response that we'll be particularly interested, and there are some bad examples on the left and good examples on the right. So one aspect of a filter is that transition width that we were talking about on the last slide, where if in this case of a low pass filter, what is the transition between the pass band and the stop band? And on the left, this transition width is about 0.2 Hz, where it's a lot tighter on this right plot. So we would probably prefer the filter with a frequency response like this, so we can have very high control of which frequencies we're passing and stopping, and not treat some components in between. Another factor is the amount of ripple in the passband of the signal. So what I mean by that is on the left here, where in the frequencies below 0.2 Hz, there is not a flat gain or attenuation of these frequency components. The 8 Hz or the 0.18 and 0.19 Hz frequency components are attenuated a bit differently, and that's not ideal. We would want all of these components to be treated the same, which is what we see on the right here, where there is no gain or attenuation for any of these low frequency components. And on the bottom, it's ideal if we have a lot of attenuation in the stop band and completely eliminate those frequencies. So now the y-axis here is decibels, where if we have a greater negative value, that is greater attenuation of the signal at a given frequency component. So on the left, the attenuation in the stop band is around negative 40 decibels, but on the right, the attenuation in the stop band is less than negative 80 decibels. So we have significantly more attenuation and would probably prefer to use this filter. So this is an example of two low-pass filters. The one in red is a finite impulse response filter, and the one in blue is an example of an infinite impulse response filter. Those are two terms that we don't really need to know for this class, but just know there are two different types of filters. And the The red filter, the FIR, finite impulse response filter, has a very steep roll-off in its transition from passband to stopband, so that's generally more ideal than the blue filter here that has a much larger transition between passband and stopband. However, the blue filter is able to achieve a lower attenuation at the high frequencies. So it's designing these filters is a trade-off between some of the properties that we find ideal. And fortunately, MATLAB has a really nice toolbox, the Filter Design and Analysis toolbox, that we'll look at now and also on the homework, that will allow us to visualize the filters in both the time and the frequency domain. So the filter kernel that will be convolved with our signal to get the output, as well as the Fourier transform of that filter kernel, which describes the frequency response of that filter. And this filter design and analysis toolbox will allow us to adjust the parameters of these filters and their classifications in order to design the best filter for our purposes. I just opened up MATLAB so we can look at the filter design and analysis toolbox. So to do that, we just, in the command window, type in fdatool, press enter, and the filter design and analysis toolbox will appear. So just fitting this, and up at the top will be a plot where we can see our filter kernel or frequency response. And at the bottom here is where we will design our filter. So the first category here, response type, are the types of filters we just went over: low pass, high pass, band pass, and band stop. So let's just design a low pass filter. The second box is the design method, where the choice is between an infinite impulse response filter and a finite impulse response filter, and each of them have a few different subtypes of filters. So let's design just a common filter, which is a finite impulse response filter using the window method. A very common window to use under these options is just a Hamming filter. Each window will give your filter specific properties, but a Hamming window is very commonly used for analyzing electrical signals in neuroscience, so let's just stick to that, and you can explore the other windows and how they affect your frequency response later if you want to. Under frequency specifications, let's just set our sampling rate, fs, to 1000, 1 kilohertz, 1 sample every millisecond, and fc here is our cutoff frequency for the low-pass filter. So let's set that to 10 hertz. So we want to pass everything in the signal below 10 hertz while suppressing everything in the signal above 10 hertz. And the last specification is this filter order, which is the length of the filter in samples. And a common practice is to choose this filter order based off of the cutoff frequency that you use. You have one cutoff frequency in a low-pass filter, and a band-pass filter you would have two cutoff frequencies, and would base off of the low one. So this cutoff frequency is 10 hertz, so the length of one cycle is 100 milliseconds, or in this case 100 samples. So in order to design this filter adequately, we want multiple cycles of the cutoff frequency to fit in the filter kernel. So let's just choose 5 cycles. So 5 cycles times 100 milliseconds per cycle, 100 samples per cycle, will be 500 samples as the filter order. And then the last thing to do is just click Design Filter, And what pops up here is the magnitude response of the filter, what I've been calling the frequency response of the filter, which is the Fourier transform of the filter kernel. So on the x-axis we have frequency, which goes up to 500 because our sampling rate was 1,000, and this is the Nyquist limit, as I believe Stacy talked about in her lecture. And on the y-axis is the magnitude of the filter in decibels. And this relates directly to how much each frequency component is suppressed. So let's zoom in to between 0 and 50 hertz. And what we see is that the magnitude in decibels of the filter is about 0 below 10 hertz, then between 10 and 15 hertz drops to below negative 50 decibels. And just a quick aside on gaining an intuition for decibels, let's just utilize a MATLAB function mag2dB. I think that's right. So this function magnitude 2 decibels, we would put in the attenuation of the filter and then output what that attenuation would be in units of decibels. So if the filter attenuated our 10 hertz component, or let's say 20 hertz component in this example, by 90%, the magnitude of the output would be 0.1, or 1/10 of the original one. And what that would be in decibels is negative 20 decibels. So up at the chart, back in the FDA tool, where we hit negative 20 decibels is around 11.8 hertz. So the 11.8 hertz frequency component here is attenuated by about 90%. Another example would be back to dB. If our signal was attenuated by 99%, then the attenuation would be negative 40 decibels. And the equation for this, that this mag2dB function is just doing, is the 20 times the logarithm of the output magnitude. So in this case 0.01. This is log 10. So the log function is for the natural log, 20 times log 10 of 0.01, and that will give you negative 40 decibels. So this is the formula for how to obtain decibels from a given magnitude attenuation. So going back to the FDA tool, we've seen our magnitude response here, where we have we pass below 10 hertz and suppress frequency components above 10 hertz. So there are also other options that you can look at up at this top bar here concerning the filters. And the other one I want to point out is this impulse response that we can click here. So this plot here is now the kernel of the filter. So what the time domain signal that actually gets convolved with your input signal in order to get the filtered output. And the y-axis here is just the value of that kernel at each point in time. And you could see here that it's looks like a sinc function or a sine wave that decays over time. It's so back to the presentation. One property that is very useful in frequency analysis is the convolution of two signals in the time domain, which is what we're doing when we're sliding a filter kernel through the signal, is equivalent to multiplication in the frequency domain. So both the input signal and the kernel, when you take the Fourier transform of them, you get a frequency representation, which on the right here, I just showed the power spectra of the input signals on the left. And this input signal is convolved with a kernel, which is a beta band bandpass filter, so it passes frequencies between 13 and 30 hertz while suppressing frequencies in the other regions. So that's represented by its frequency response is high in the beta frequency range and low elsewhere. And when you convolve these two signals, you just extract the 13 to 30 hertz oscillatory component in the output. However, if you look at the frequency domain representations of these three signals and were to multiply them point by point, so the 5 hertz component of the Fourier transform of the input signal with the 5 hertz component of the Fourier transform in the transfer function would yield the 5 hertz component in the output signal. And you can see this also similarly just by looking at their power spectra, where the input signal has this complex power spectra that has a peak in the beta frequency band, but also has significant power elsewhere in the frequency domain. However, after convolving in the time domain and multiplying in the frequency domain with this filter that only has power in a narrow frequency range, then our output signal will only have power in the narrow frequency range, while these components in the input signal were multiplied by very low values in the high frequency and low frequency, and so the power of those low frequencies and the high frequencies went to 0. One other important thing to know with filtering is concerning edge artifacts that can appear in filtering. So the signals that we deal with are all finite in duration. So let's, given this example data here that we want to do a low pass filter on. And then in the middle here we have the filtered signal, but zooming in on these edges, you can see that the low pass filter didn't work too well for the beginning of the signal and at the end of the signal, and this is what we call edge artifacts. And the theoretical duration of this edge artifact is half of the filter length. So earlier when we designed the filter that was 500 samples in length, that edge artifact on each side would be 250 milliseconds. And the reason for this is that if we align the filter kernel so that its center is 250 milliseconds into the signal, then it will span the signal completely, and so there shouldn't be any artifacts. However, if we center the filter kernel at within the first 250 milliseconds of the input signal, then part of the kernel will just be multiplying zeros out here where the data has no value. And so since that isn't really a true signal that's being processed, we get these sort of artifacts at the beginning and end. And the best way to get around this is to not epoch your data, not limit the amount of data that you're dealing with before you filter. So if this 1.5 seconds was the duration of a trial, you will likely have recordings before and after that trial. So keeping that data in there, the data before and after the trial, when you're filtering, will allow you to not have these edge artifacts. So if you look at the fine blue, dark blue line here, you can see that it no longer has edge artifacts as the filtered signal had in the finite signal case where we only had the signal within the trial. And a couple of final notes on filtering is just how these principles can be expanded for two-dimensional filtering. So up to this point, I've only been talking about filtering in one dimension, just one electrical signal that's a function of time. However, images are also commonly filtered, and they're two-dimensional in shape, so they have a value for every x and y component. So a low-pass filter for an image would look something like this inset here, where the center of this plane is 0 for x and y, and the filter kernel will have the frequency response of the filter will have high values close to 0, close to low frequencies, and will suppress the high frequencies in x and y. And the effect that has is smoothing the picture, so looking at the headlights, it's a lot blurrier. Also, another example would be a high-pass filter, where instead of passing the low frequencies, you suppress the frequencies around 0 in x and y, and don't suppress the high frequencies. And the output that you would get from this image of the car would be all of the rapid transitions between white and black, the high frequencies in that picture. So in the second part of the lecture, we'll talk about amplitude of oscillations. So this is an example signal that I showed earlier, in which we have the raw trace on top and a bandpass filtered signal on the bottom in the alpha frequency range, so between 9 and 11 hertz. And you can see that this alpha oscillation is changing in amplitude over time, and that might be meaningful for the data that we're analyzing. That might have some physiological meaning that we're interested in, so we're going to go over how to calculate these amplitude changes. So one example of an amplitude change is what's called an event-related desynchronization. So on top here we have a plot of finger flexion. So the blue trace is a measurement of how much the thumb of a person is flexing. So around this time point, the person starts moving their thumb. And in this case, that is the event that we're interested in. So we see right before this event where they start moving their thumb, the frequency profile of the neural signal on the bottom here changes. So on the x-axis here is time, the y-axis is frequency, and the color axis is the power in each of these frequencies. So it's very similar to the spectrogram that Stacy went over last week. And as you see over time, at the beginning of the trial, there's relatively high power in the low frequency range. So maybe this is a beta oscillation between 10 and 30 hertz. And there's relatively little power in the high frequency gamma ranges. However, right before this event, the thumb flexion, these beta oscillations essentially desynchronize, and by that we mean that the power in this oscillatory range decreases, while the power in the high frequency ranges increase. So this is illustrated by the plots on the right here, where these two low frequency ranges, the theta band and the beta band here, they show that this black bar is representing a lack of movement, while these three colored bars are the movement of the fingers shown on the bottom here. So when the thumb moves, the low frequency power in these two bands decreases. However, if we look at the broadband amplitude, or the amplitude across the frequency spectrum that includes the high frequencies, then we see specifically at this electrical recording that the broadband amplitude increases most for the thumb flexion. So what we're going to specifically be talking about is the amplitude as a function of time of a specific frequency range. So for example, the amplitude in these low frequency ranges decrease after the event. So this is another visualization of an event-related desynchronization where EEG is being recorded in the electrode indicated here, and before the stimulus there's a very strong oscillation at about 10 hertz that we see in this time frequency plot here, indicated by the dark red color indicating high power. However, that 10 hertz oscillation is desynchronized after time 0, after the event occurs. So if we were going to calculate one of these time frequency plots in order to do an event-related desynchronization analysis, there are a few steps that we're going to go through that are outlined here, and I will go through each of these steps one by one. Before getting the amplitude, we first will do a wavelet transform on the data, and I'll go through that now. So before getting into a wavelet transform, let's look at the specific wavelet that we're going to be using. And the wavelet that we'll go over today is called the Morlet wavelet, and that is the blue line here. So it's a sinusoid that's decaying as you get away from the center of the wavelet, or the filter. The wavelet in this case is your filter. And what's special about the Morlet wavelet is that it is the product of a sinusoid. In this case I think it's 50 hertz with a Gaussian distribution. So the sinusoid is in green, the Gaussian is in red, and its product is in blue, the Morlet wavelet. And so that was in the time domain, and if we look at the frequency domain, as we mentioned before, convolution in the time domain is multiplication in the frequency domain. The opposite is also true. This is multiplication in the time domain is equivalent to convolution in the frequency domain. So the green and red signals are being multiplied in the time domain. The green signal is shown here as just a impulse at 50 hertz because it's a pure sinusoid, whereas the Gaussian in the time domain is also a Gaussian in the frequency domain. So when we convolve this green impulse with a Gaussian, what we end up with is a Gaussian frequency response, a Gaussian frequency profile of the blue wavelet. And the wavelet in the time domain has a Gaussian distribution as a function of frequency. So this is just a few examples of Morlet wavelets for different frequencies. This top one is 5 hertz. Notice that it's longer, more spread out than the wavelets at 10 hertz and 20 hertz. So when we have these wavelets calculated, which most programs such as MATLAB and Python will just have a function for you to generate these wavelets. You will then do what's called a continuous wavelet transform, which there will also be a function to do this between your input signal and a wavelet at each frequency. So this is just an example where we're multiplying the input signal, or we're convolving the input signal with a 20 Hertz wavelet, and what we get in the output is the filtered version of the input. So the real component of the wavelet shown in the solid line, and the imaginary component of the wavelet is in the dotted line. And these two components are treated pretty much independently in terms of the convolution. So the real part of the wavelet convolved with the input signal will give you the real part of the output signal. And this is essentially very similar to just a bandpass filter around 20 Hertz. And the imaginary component is the convolution with the imaginary component of the wavelet with the input signal, and that's just looks like a little bit of a time-delayed signal compared to the real signal, and these two real and imaginary components will be useful for calculating the amplitude. So that's the next step, is how do we calculate this amplitude envelope in red from the real and imaginary components of our wavelet transformed signal. So for that, to gain intuition for that, we'll look at the real imaginary plane, where each point in time can be represented by a vector in this plane. So if your imaginary component was 0 and your real component was 1, you would lay here in the plane, and that is specifically what we see at this time point highlighted in green, where the imaginary component is 0, real component is 1, and therefore the amplitude or the magnitude of this vector is 1. So in contrast, if our real component was 0 and our imaginary component was 1, as it is at this yellow line here, then we would lie at a 90-degree phase from the real axis directly on the imaginary axis. However, the amplitude for that time is still equal to 1. Similarly, we could look at a time point where both the real and imaginary components are non-zero, and we would still plot that vector in the complex plane and take the magnitude of that vector in order to get the amplitude at that point in time. So in order to calculate this amplitude envelope, we're just taking the magnitude of all of these complex vectors at every time point. So notice that if our imaginary component is very negative and our real component is 0, we're going to get an even higher amplitude, as shown by the red line here and the extended blue arrow here. So that is all just for the 20 Hertz wavelet, in which we got this red amplitude envelope as a function of time. But with the continuous wavelet transform, we not only convolve our signal with a 20 Hertz wavelet, but wavelets at any frequency that we desire. So in this example on the right, we convolved the input signal with wavelets between 5 and 50 Hertz at a step of 1 Hertz in order to get this time frequency representation again, where we have time on our x-axis, frequency on our y-axis, and the amplitude of that frequency component shown in color. So I highlighted the 20 Hertz component here, which aligns with the amplitude envelope that we calculated from the convolution, where it starts high at the beginning of the signal, then the amplitude goes about down to 0, but then it has a little bump at the end. So we see by this lighter blue here, and this increased amplitude here. But again, that's performed for every wavelet for each at a different frequency. So if we're interested in calculating a difference in amplitude between two conditions, one possible way we could do that is by designating sections in this time frequency profile that will average the amplitude over. So, for example, if we're interested in the beta amplitude between 10 and 20 hertz before and after an event at time 0. So we would choose the frequency axis to range between 10 and 20 hertz, and the time axis, for example, to go between negative 500 milliseconds and negative 250 milliseconds, and positive 250 milliseconds to positive 500 milliseconds for the other epoch that we're interested in. So the reason why we don't want to get too close to 0 here is because, remember, filtering in essence smooths over time, so we want to have at least half of the kernel width between the data that we're analyzing and the data that we don't want to analyze, or in this case, for epoch 1, we don't want to include any of the data after time 0. So that's why we don't analyze the amplitude all the way up to time 0. So we could take this matrix of amplitudes for a chunk of time and a chunk of frequency and average all of those in order to get a single value for the beta amplitude prior to a stimulus. And we can do the same after the event in this white box to average the amplitude for this time and frequency period. So now we have one amplitude value for each trial before and after the event. So we can do a statistical test between these two populations to see if they're significantly different. And the way to do that is we can estimate that these are normally distributed in this case based off of these plots and how I generated them. Since we're looking at a single trial for getting a data point from both before and after the event, this would be a paired t-test. So by doing a paired t-test between these two groups, we would see that there is in fact a significant decrease in the beta amplitude after the event. So one thing to keep in mind is that you could do this analysis, but have an artifact in the data that could yield confounding results. So in this case, the artifact is just a sharp transient in the voltage at a time point that would yield power in all frequencies. So if you looked at this plot, it may seem like the alpha amplitude is not changing from before and after the trial, but in fact the supposed amplitude between 10 and 20 hertz coming after the trial is really from a sharp transient that has power in all frequencies. It is not a genuine alpha oscillation, and so the power in these two bands is not really representative of what is going on before and after the stimulus. Sorry, I kept saying alpha when I meant to say beta. So as I mentioned previously, this wavelet convolution method is, since it's filtering, it's smoothing the data, so it wouldn't really be accurate to test two epochs that are very close together or adjacent in time, because the same data is going to get smoothed out and be present in both epochs. So you have to be careful with filtering to make sure that your analysis methods make sense and you're not reusing the same data. So that's all for this lecture, where we talked about the different types of filters, how we design them, and then went into the amplitude envelope and how we calculate that with Morlet wavelets. So in the next lecture, instead of talking about the amplitude of frequency components, we're going to be talking about their phase and also some applications in neuroscience, such as calculating the coherence between the oscillations in two brain regions.